Welcome back to another dynamics video. Today we're going to do absolute and relative acceleration. We're going to do 3 examples. I'm going to try something a little different. I've already put together the slides for this, so hopefully I'll be able to go through 3 examples relatively quickly. If I go too fast, obviously you could just pause or rewind the video. So instead of taking the time to write everything out, I'll just click here, and then I'll try to explain and walk you through the solution. I've posted these solutions as well as in PDF on the D2L page for my class. All right, so here we have a piston and rod connected to this disc. You could think of this as very similar to an engine, where this would be the crankshaft right here. So what we're trying to find is the angular acceleration and the acceleration of B. So remember that we have to perform a velocity analysis every time we do an acceleration analysis. So we start with the disk, and because it's a fixed piece here, we don't have to do the 3 diagrams that we'll do for other things that have both translation and rotation. This disk only has rotation. So about its center, it's rotating at 3 radians per second. It's also accelerating at 8 radians per second squared in the same direction. So we could find the velocity of A by multiplying that 3 radians per second times the radius right here, which we've seen to see is 0.2 meters. So we get the velocity of A. We could also find the acceleration at that point, this point A right here. We could find that because it's in the normal direction, it's rotating at that 3 radians per second, and we could find that with the 3 radians per second squared times that radius again, and I believe that should be a 0.2. Excuse me, I messed up the on the number there, and we will get 1.8 meters per second squared in the normal direction. It also has a tangential acceleration due to the angular acceleration. So we want both of those components of acceleration at that, and we take that angular acceleration and multiply it by that, again, by that radius, which again I messed up and wrote that the wrong way, so I'll have to correct that on the posted solutions. So we get 1.6 meters per second squared, and that's to the right. Okay, so we do a velocity analysis on the rod. In this particular situation, it just so happens that if we do a velocity analysis, we're going to find there's going to be no angular rotation. Well, how do we know that? Well, we could take a look at and apply the velocity that we found here of an A and apply it to the diagram, and we can see that's completely in the horizontal direction. And we can also see that B is constrained, so it can only move in the horizontal direction. If that's true, there can't be any rotation, because a rotation would cause, in this case, a Y direction velocity. And since there isn't none, these have to be equal to each other, or they have to be in the same direction. If they're in the same direction, they have to be equal to each other. So the rod is in pure translation. So it's the velocity at B is equal to velocity at A. Long explanation, but we have to be careful. We can't always assume that that's going to be the case. If it was in a different angle, at a different point along the rotation here, we would find that the rod would have some angular velocity. All right, now we have to do an acceleration analysis of the rod, and here we have the standard way where we break the thing down into translation and rotation. And I separated out this equation that we go to for the relative motion. I've separated it out underneath the diagram so you could see kind of how it's broken down and the associated parts of the equation with the rod. All right, so first thing we do, we apply the known acceleration that we just got from the disk onto that part A. And we take a look at point B, and truth be told, we don't know whether it's accelerating upwards or accelerating downwards. We just know that it has to be accelerating along that line. So following our equation here in the second part of the diagram, that's the translation. So we're going to use A as our reference, and so we're going to apply that same acceleration to B, so that that's the pure translation portion of it. And then over on the last part of the diagram, we pin that reference point A, and notably, once again, that it doesn't have any rotation on it. Because it doesn't have any rotation on it, there's not going to be any normal acceleration, right? Because the normal acceleration, remember, was omega squared times r, but we don't have any omega, so we can't have any normal acceleration. But we do have tangential acceleration of some sort. Now we have to have some tangential acceleration because if you think about how we have a y component right here, that y component needs to disappear in order for B to be completely horizontal. So in this case right here, we're able to tell that this has to have an upward portion to it, this tangential acceleration, in order to counteract the downward portion of y here. All right, so we break the thing, and it's going to break the thing down into components here. Notice that I could easily transform that acceleration that we had previously. We called it as normal and tangential. Because they happen to align with the x and the y, we're able to just go ahead and just change what we're calling that into x and y. Might have to do a little bit of sines and cosines of those components if they weren't necessarily aligned. But for most of the time, if you just stick with if you try to be a little strategic in the way that you lay the thing out, you'll be able to just make that kind of jump. All right, so in the y direction, I've rewritten this equation out for that component, and I've been a little bit careful here to emphasize the fact that, and we'll see maybe in another problem that this is an important thing to consider, that the y direction, the tangential and the normal components don't necessarily coincide with the x and the y. So we have to be careful we don't just apply them to the x and the y as if they're already broken down. We have to break down the y component of the tangential and the y component of the normal, if that makes sense. Hopefully you'll see it. In this case, it's we're lucky enough that there's not many things going on in the y direction. That's why we're solving for it first. We know that the acceleration of b in the y direction is 0. Acceleration of a in the y direction, we already have that from the previous page where we did the acceleration analysis. And now we take the angular acceleration here, and that's what we're trying to find in this first step. And we can multiply it by this radius because that's the tangential component is alpha r. So we have this alpha AB that we're trying to find times 0.4, which is the radius, or I should say the length. That's the r that we're dealing with. That's about this point right here. So it's this length right there. And the times 60 degrees because it's only going to be in the vertical direction, the vertical portion of that tangential one. And if we do that, we find that we get an angular acceleration of 5.196 radians per second squared. And notably, that's going to be in the counterclockwise direction. Okay, in the x direction, we're able to do the same thing, but this time we're going to look for that AB. So by the way, this is like the first part that we were asked as part of the problem, so that's actually one of the answers that we want to block off. So the acceleration of B is the entirety of the x component here. And so we take 1.6 because that's the acceleration we found in the previous one for the, I believe it was the tangential acceleration of the disk, which is now the x direction of this. And we add it to that angular acceleration right here, which this is the alpha, and then times 0.4, which is the distance there of the rod, and then taking only the x component of it, like right here, okay? So it's also positive because it's going to the right. I also put a 0 in here to represent that as a placeholder to see that there's no normal acceleration. And we end up with getting an answer. So that's the other portion of it. It's not it's not a simple problem, but you can see that there's a process we can march through. Now for this next problem, this comes from Schaum's Outlines from an earlier edition, the 5th edition. This was a practice problem where they didn't give you the solution in the Schaum's Outline, but they did give you an answer. So let's break the thing down and go through it again. First thing we need to do a velocity and acceleration analysis of the disk. We're going to use instantaneous center of rotation to do the velocity portion of it. So we're going to treat the point where it's touching the wall as being its instantaneous center of rotation because that velocity is 0 there. And we're given that it's going 12 feet per second downwards down the 30-degree inclined plane right here. And so we know what the velocity of a point I'm calling C is going to be. And with that, we're able to get out the angular velocity, omega C, of this disk by dividing that 12 by the radius there, which is going to be 2 feet right here. This amount. Now we're also able to get the velocity of B by using that same equation for the omega, but this time times the radius of B with respect to D. So it's going to be this entire radius right here relative to our instantaneous center of rotation. And we get that to be 24 feet per second. And because they're saying that it's rolling at a constant velocity, that means it's going to have no angular acceleration. So that's going to be 0. So the tangential acceleration is going to be 0. But there is still going to be an acceleration due to the fact that it is spinning, right? And so we're going to use as it's rotating about point D, so its acceleration is going to be based on that the 4 feet, as opposed to doing just the radius right here. So it's they have that angular velocity of 6 radians per second that we found squared times 4, and we get 144 feet per second squared, aiming towards the point D. Okay, now we want to do a velocity analysis of the rod. Now the rod is moving with that velocity at point B equal to what was going on with the disk. Point A, this is sliding down that wall, which let's see, I'll go back to this, which you notice is 60 degrees up here. Okay, so going back in there, so that's the wall that it's sliding down. If we draw a line that's perpendicular to both of these velocities, okay, so the velocity at A can either go up the wall or down the wall. We might not be able to tell just from intuition what that is. I mean, we possibly could, but we want to double check it anyway, even if our intuition can sometimes be wrong. So we find that the intersection point between those two perpendicular lines that were drawn to the velocities gets this ICR right here, which is going to which we could find just by taking the angles that we were able to establish from the geometry, and we're able to find this distance right here, I believe, B right here. So we're finding that right there, and if you take a look at what the velocity gets, velocity of B, you can see that it has to rotate clockwise to be about that ICR, and therefore you're going to be able to tell that the velocity of A is going to be climbing up the wall. And we're able to find what the rotation is of this rod. Now, it just so happens it ends up being 6 radians per second, but that was not something that's going to be guaranteed simply because the disk was moving at 6 radians per second. In fact, this is moving in the opposite direction. So just be aware that it's just a coincidence that they're the same magnitude. Okay, so we go to an acceleration analysis of the rod. By the way, we could have, if we wanted to, gotten the velocity of A, but we don't need it for this analysis because we can just use the omega of it for our purposes. The rod acceleration analysis, we begin in the same manner that we generally been doing, where we break the thing into translation and rotation, using B as the reference. And we're going to have 2 parts of our relative acceleration, the tangential and the normal. So we put in the acceleration we found from the previous of the disk, and noting that the geometry of it. And then we have the geometry of the wall, and the acceleration has to go either up or down along that wall. Once again, we might not know what that is, but I think in this case we're going to go ahead and assume one, but let's see what I did here. Now I take that acceleration at B because it's my reference, and I'm going to apply it to both A and B to represent my translation. And I'm going to pin B because it's my reference and move about it. Now I already found my omega AB, and I'll be able to find what my normal acceleration is because of that. And then also we'll have an angular acceleration, and I'm going to go ahead and I'm going to guess that it too is going to be clockwise, but I don't know that to be true. And if that's the case, I believe what I'm saying here, well, I don't necessarily know that this is true. Actually, I find out later that that's going to be true, so I'm kind of jumped the gun by drawing that in there. So we go to the acceleration in the x direction, and in the same way, I've tried to emphasize that the acceleration and the tangential acceleration and the normal acceleration can have components in the x and y. So you actually have to be careful to take those and break those down into x and y components. It doesn't end up being that torturous. It's just something that you're going to have to notice that in the way that I've written out there to be entirely clear that you need to break the thing into components itself. And it seems a little strange because it already seems like it's in components, and now you're going to be breaking it further down into other kinds of components, but it's necessary to do it. So we have the acceleration of B in the x direction, and we have the tangential and the normal components here. So what we do here is we're going to take and just say, hey, okay, we're going to find the magnitude of the acceleration of A, and I think I've assumed that it went downwards right here as part of this. And so it's going to be in the positive x direction, and we're going to take the sine of 30 degrees to get the thing. And we have over here, we already knew that it was 144, and we'll take the sine of 30 degrees and say it's to the right. And we'll add in here, and we'll say that, okay, this, yeah, right here. Okay, excuse me, I want to backtrack in a second. We take, it has no angular acceleration component in the x direction. Let's see, I say that wrong way. It has no tangential component in the x direction because of the way things line up. And that's kind of a nice arrangement for this particular problem. It simplifies it. But there is going to be some normal acceleration in the x direction. In fact, all of the normal acceleration is in the x direction, and that's omega squared times r, of course, and I'm using this as symbols of A with respect to B because B is the reference. And then so I take 6 squared times 8. Right, and I also notice that this acceleration that I had here is what I'm backtracking down to, is that the acceleration of A had to be in the down the slope direction because the only it had x components of B were in the positive x direction, and it had components of n that were in the positive direction. So it had to go to the right somewhat. So its x component had to be to the right. So it had to go down the slope. And so we solve for the magnitude of a, and we're able to find the acceleration of a. Now, knowing that when we do go to the y direction, we're going to be able to find what this angular acceleration is going to be, because we could take the y component of now that acceleration that we know, and we know it's downward, so it's negative here, and we're going to apply the portion of the y direction of what we'd already found for b right here, and then we're lastly going to have our alpha times r. So it's the alpha times r term right here is going to contribute to that. But once again, we had to guess the direction of that. We didn't necessarily know it. Right? So once we calculate the thing out, we find it's a negative 62.35. So we guessed wrong. But that's okay, because now we just correct it, and we end up getting an answer. All right, so here's the last, and by the way, just point out that these answers match what Sham's outlines says that you should get. Lastly, here's a problem. I think I adapted this one just because we had so many piston problems that were arbitrary angles. So I wanted to make one, or not arbitrary angles. We had them where they were 0 or 90 degrees, and they ended up being special cases. So I wanted to make one that was a little bit more complicated. And so here we go right here. First I get the angular velocity of the thing and find this 94.25 radians per second from the 900 revs per minute. Now here's my velocity analysis. I did both of them at the same time here, and I find that the velocity of B is going to be 188.5. And using, I have to do a little bit of trigonometry here. I want to find this angle beta right here, so that I can use that to find the locations of my, or the lengths of stuff with the ICR, so I can find out what my angular velocity is. So I found that beta, that angle, so that I could find out what this angle is right here. And I find that to be 73.22. And now I can use law of sines again, and this time use law of sines along with my 6 inches of the connecting rod, the con rod, and I'm able to, with that, to be able to find what this length is right here. And that length is going to be useful to us, because now we can find what the angular velocity is of this whole piece. And so we're finding that has an angular velocity of omega BD based on what the velocity was that we found at the common point B. Right. Okay, I guess I decided not to make the animation here at point by point, so it looks like there's a whole lot of things here, but let me just talk you through this because I've gone this far. All right, so the acceleration of B, right, can be found just because this thing is on a fixed point, and it's rotating at a constant RPM, so the only acceleration is the normal acceleration that's going on here. And so I can find that, and it's 17,776 inches per second squared, and it's going towards the downwards towards the center here, which I'm pointing out to you is 30 degrees downwards. Now, the acceleration of the connecting rod, I can write it out in a number of ways, and here's a different version of what I had written before, recognizing this is the tangential and this is the normal. And but I've put it, this is the same equation in vector form with showing the cross products. So in the x direction, because I'm using D as the thing I want to find, I'm using B as my reference right here, right? B is the translational portion. I could say that, okay, the acceleration on right here in the x direction of AB is going to be the cosine of 30 degrees, negative because it's to the left, minus the okay, so that was actually this portion right here, right? So, okay, but I'm looking up here. That's correct. I'm sorry. So I should be drawing it up here, right? So here is the 0 right here. It's up here. Nothing going on. And then here is the x component right here of that. And then there's going to be a contribution both of the tangential and the normal, right? So the tangential's contribution right here is going to be times the cosine of that 16.78. That was to end up being the same angle as beta. And it's also going to be sine times that because we want to get the x contribution here of that. So right here we find that, well, of course, I'm just breaking it down step by step here, where I have the tangential and the normal is alpha r and omega squared r, respectively. And plugging some numbers in here, I end up getting an alpha of equal to negative 2,599 radians per second squared. It's because it's negative. That means I selected my initial guess, which was to be counterclockwise here, is incorrect. So it actually is clockwise, that angular acceleration. Now, knowing that, I can go to the y direction, and now I can complete my problem by finding that the acceleration of this piece right here, I end up finding that it's going to be in the downward direction of negative 5,946 inches per second squared. So that's what ends up being the answer right there. I know it seems like a really long and involved process right here, but it's really, it's just taking the time, being very careful and methodically marching through the problem. I mentioned that there's this has wide amount of applications. This technique that we're using here is just one of many that you can apply to try to find to do acceleration analysis. So you might find in mechanisms course we have several other techniques that we use. And some are better than others for turn into computer programs to try to solve problems. So this is not maybe the best type of method to apply to try to solve any kind of problem as a general solution method. But it is an effective one, and it keeps that idea of the relative acceleration and relative velocity as something that you can use as you march through a piece so that you could find the information that you want. So hopefully this will help you in doing the homework problems, and I hope everyone had a really good spring break. I know that you probably purged a little bit of this knowledge, but let's get back in there and do that next homework problem, that IEP, and let's go gangbusters on it. Have a good one.